Ultimately, we want to use our data to make conclusions that something is occurring logically and consistently or reliably, rather than by chance. In statistics, we always seek a certain threshold of certainty to make sure that the data we are analyzing suggests a pattern that is not occurring by chance. Again, we're looking for meaningful differences. If I have a class of 100 people and 51 failed my test, should I be concerned? Yes. Because of the context, we would never want a teacher or class that was failing at a rate of 51%. However, if 51 students said they liked pizza, while 49 said they did not, could I generalize to all students and say that more students enjoy pizza than do not? No. The difference in the amount of people that like pizza and those who don't is not very large, just 2 people. We need to be able to find the difference between these 2 groups that is substantial enough of a difference to not be affected by just one person's mood on that day. We need to know that the magnitude of the difference, the size of the difference, is large enough to make predictions about other groups of people or generalizations about populations. Let's take a look at the decision tree in the book. It's unlikely in this course that we will get from the far left side to the far right side, but I want you to know that there is a pathway to making a decision about what to do with any type of data. In the beginning, we would look at whether the data is qualitative, which normally refers to words, or quantitative, which normally refers to numbers. Based on that information, we would move on to the type of categorization or type of question that we would ask, variables that we would choose, and groupings. Ultimately, we would decide on the type of statistical analysis that would be most appropriate for the data that we have and the research questions that we're asking. Many of you, I'm sure, know what quantitative data is. It's what you're used to. Many of the surveys that you have taken in your life are measured with numbers. Many use Likert type scales that ask you to rate your agreement on a scale from 1 to 10. Or they ask how many times you've done something, or they ask how tall you are. These are all examples of quantitative data. Just for your records, the book calls quantitative data measurement data. However, it's unlikely that you'll hear this usage often in life. Most professors and researchers refer to it as quantitative data. That's right. The book also talks about something called categorical data, also known as frequency data or count data. This involves times when we are counting things such that we describe the totals or frequencies for each category. Again, I will not place much emphasis on this type of data. When frequency data is used, I normally do not separate it from other types of quantitative data. Regardless of what we call quantitative data, we make one key decision as we determine what we want to know about the data. Are we interested in a relationship between variables, such as the frequency of using e-cigarettes and the frequency of developing lung cancer? That would be a question about a relationship or association. In contrast, are we looking at 2 groups of people that we think may be different? By different, I mean that both groups represent their own unique population. If I want to cure cancer and I want to show that I have a reasonable means to do it, I might give my drug to 500 people and give something that looks like my drug, a saline solution, to another 500 people. I could watch all 1,000 people for 1 year, collect data every 3 months, and determine if cancer decreased or remitted more so in the group that was treated with my drug. In this case, I would be looking for a difference between the 2 groups. Qualitative data is different. If I interview 10 or 20 of the people that took my drug to understand what it felt like, what side effects occurred, how consistent they were in their usage of the drug, I'm collecting qualitative data, data in the form of words. In most cases of qualitative analysis, I'm looking for similar themes. If I hear about a side effect from just one person, I may consider it to be an outlier or a discrepant case or some random occurrence. However, if 19 of my 20 interviewees mention the same side effect, I have a theme I should pay attention to, a consistent problem with a particular side effect. Similarly, all participants might mention that the drug made them feel energized, or that they all had difficulty taking it 3 times a day. All of this information is useful. On this slide, we see an example that is not experimental. We are not doing anything to the teams to make them smarter or work harder. Rather, we are trying to understand the difference between naturally occurring groups of people. It's important that we put our own personal biases aside as we do so. So we might be interested in the difference between Chinese and British teams on a math test. Read the book Outliers by Malcolm Gladwell for information about how the Chinese language makes math easier for the brain to compute. I might also be interested in the relationship of height to mathematical knowledge. I'd be surprised to find any relationship here. A relationship could be that taller people do more poorly on math tests, or that as people get taller, their math abilities increase. Certainly this is true among school-age children who are growing, and as they do, acquiring better math abilities. But after age 18, height would be an unreliable predictor of math ability. It's important that we have a reason to test something, a theory or hypothesis that supports the difference that we're trying to find, or the relationship that we're trying to find. Let's look back at the decision tree. The statistical analysis that we will choose is often based on how many groups are to be considered, or the number of variables that we will analyze. Something called a t-test is used only when there are 2 groups of subjects and not more, whereas an analysis of variance, or an ANOVA, can be used with more than 2 groups. The type of data that we are looking at also matters. If I assigned a number to each eye color, and then counted the number of people in this room with each different type of eye color, could I then take the average of all the eye colors? This wouldn't make sense. There is no average eye color. There might be a most common eye color, which is something called the mode. The numbers ascribed to the eye colors were done randomly and without meaning. The only useful information we could get would be to count up the number of people with each different eye color and provide a number of the frequency of that eye color occurring. I'll meet you back here at Chapter 2 very soon. Thank you.